ran across this paper recently in the latest issue of JACS, Journal of the American Chemical Society. And it's one of these organic synthesis, total synthesis papers. So it's one of those that gets all the organic chemists just a quivering inside. But you'll notice from the title, it uses a transition metal catalyst, rhodium, as part of the synthesis of the stuff they're trying to make, a compound called Brevicin. So it gets the inorganic chemists, they're a little wonky people, I know, but it gets the inorganic people just all happy about it as well. The compound itself is actually a natural product. It's extracted from some sort of marine organism, so the biochemists and the biologists are all in the game. As you might guess, to extract out this stuff from a marine organism and to purify all the different stuff you have to make in the synthesis, the analytical chemists are in this game as well. There's an awful lot of separation type stuff going on here. And if you're going to do this type of work, for example, try to synthesize a natural product that might have, let's say, medicinal type properties, you must first do a full characterization of it. You have to know, if you're going to try to make it, exactly what the structure is. The stereochemistry, the number of carbons, the hydrogens, the whole 9 yards. And I'll give you one guess as to which technique is used to do these characterizations. And if you just said IR spectroscopy, I really should go over there and beat you with a wet spaghetti noodle, because no, that's not the one. A full characterization essentially means what you're going to do is you're going to acquire the spectra on this compound, and you're going to assign every single proton to in the structure to every single peak you see in the proton spectra, every single carbon to every single carbon peak. In other words, you're going to prove to the rest of the world that this structure and only this structure can match this set of spectra, and that you've analyzed it down to the umpteenth detail and you have this thing nailed down. So here are the molecules, Brevicin at the top here and some of the precursors down below. You can see they're big old cyclic molecules, natural products. Oh, this would be just this horrible, messy set of NMR spectra, and it is. Now I want you to see a couple of things from this. The supplementary material to this paper is over 200 pages long. It's extensive. It's some of the most extensive that I've ever seen. And the work that put that thing together, it's got to represent, several graduate student half-lives. Who cares, they're graduate students, but there's an enormous amount of work represented by this one paper and in this one project for synthesizing this compound. One of the spectra is this one here. It's an HSQC spectrum. By gosh, we're starting to get used to seeing these things here. I just wanted you to see that here it is, a 2D NMR spectrum, a technique that we're just learning about, and to show you in a paper published early June 2015, this spectrum was a component of this paper. This is some of the work being done on the frontiers of our field right now. The other characterization data, yes, you do have all the protons and carbons assigned here. Oftentimes they give you all the spectra, but they'll also summarize it in these long lists of texts and stuff. Here's what this stuff looks like. I'm going to go back to the HSQC for a moment just because it's prettier to look at. And I do want you to realize, as we've said a few times already, living, breathing quantum mechanics. No, I didn't forget about our friends, the P-chemists and the physicists. They're in this game too. I want you just to realize, stuff like this, we break up our science into all of its different little categories. And yeah, we like to make jokes about the other ones just because it is kind of fun. But realize, really, this stuff requires every single technique and tool in the chemist's the chemist toolbox at our disposal, and connections to all the other different sciences out there in order to do this sort of stuff. Everything is really coming together when you do work like this. Now, we're not going to examine the NMR spectra of Brevicin or anything that complex. you should be in a position when we're done with this class, even now, to be able to look at this paper and get a glimmer of how they did their NMR work, how they reached a lot of their conclusions. I mean, this is extraordinarily sophisticated stuff, but you are in a position to start to see how this is done out there on the frontiers of our science. We are going to do a full characterization of a natural product, though, a much simpler one, menthol. It's the peppermint extract. And in fact, we are going to look at the spectra that you saw acquired several weeks ago in one of the introductory videos, where I took the peppermint extract and went down to the instrument, show you a little bit about how the instrument operates. It's time to look at those spectra. What we are going to do is we are going to take the structure of menthol. We are going to label it. So we have proton A, proton B, carbon A, carbon B, and so forth. And we are going to attempt, using all the spectra, to characterize it. In other words, to fill in this table so that we have assigned every proton in menthol to every peak we see in the spectra, every carbon in menthol to every peak we see in the carbon spectra. We're going to do a full characterization of a natural product. It'll be one of the crowning examples of the power and the use of NMR that we are going to get to in this class. So here we go. When you have a big task like this with an awful lot of pieces floating around out there, it's always a good idea to start with the simplest things you have and with some of the basics, the things you know. I'm not going to start this process with the 2D spectra. In fact, I'm going to begin with the carbon and the depth results. Because one thing you want to do is just make sure that if you're going to do a full characterization like this, that your proposed structure, and let's face it, menthol structure is known, that the proposed structure and the spectra match up at least superficially. That means I'm going to look at the carbons and count the number of carbon peaks and make sure it matches what I would expect from the carbon spectrum. I'm going to use the depth spectra and count the number of quaternaries, the number of CHs, CH2s, and CH3s, and make sure they match what I expect to see out of the structure. So that's where I'm going to begin, is actually at the carbon spectra, and just make sure that the spectra and the structure match up fairly nicely. And when I examine the depth spectra, I find I have 4 CHs, 3 CH2 groups, 3 methyl groups, no quaternary carbons, 10 carbons total. And if you look at the structure of menthol, all of those are exactly what you would expect to see. So we have a nice match here between the structure and the spectra. We've gotten ourselves a bit oriented, and there's one other critical thing to do by looking at the carbon and the depth spectra, and that is take the HSQC, as yes, we are going to make extensive use of it, and put the depth results in. In other words, before you even examine any of the spots, any of the correlations on the HSQC, make sure the HSQC looks like this one, where all of the depth results, exactly which carbon is a CH, a CH2, or a CH3, have been written in. Now that we've taken an inventory of some of the basic pieces using the carbon and the depth spectra, we're going to go after some of the easy characterizations in this molecule. And to do that and to help me with it, I'm just old-fashioned enough that I just love to have the plastic with me. I mean, just give me that old-time plastic as far as I'm concerned. And so I've got the molecular model here. I'm using the blues to represent the methyl groups, the red for the oxygen, and then all the other hydrogen positions here with just the sticks coming out. And among the positions here that I think are fairly obvious is this one right here. This is on my labeling scheme, proton F. This will be the most downfield one because it is the hydrogen on a carbon closest to the oxygen. And sure enough, we do have one right down there, 3.4 to 3.5, kind of on the upfield range of what we would expect here, but within reason or something. And so I am pretty confident that I can see proton F. And if I look carefully at proton F, it seems to have a triplet of doublet-like appearance to it. Triplet of doublets, 2 protons here, 1 proton there. We must have 2 of these coupling constants nearly the same to give a rough triplet, and then a doublet for 1 coupling constant must be quite a bit different than the others. And then I use the HSQC and its ability to correlate to find the carbon that proton F is attached to. Carbon F down here, and it's no surprise, it correlates very nicely to a CH and the most downfield CH that we see in the carbon spectrum. It's no shocking surprise to see that, but it is nice when it works out. There is another proton that's going to be pretty obvious, and that's this one over here, the hydrogen sitting on the oxygen itself, technically the alcohol proton. From the HSQC, you can see this one here has no correspondence on the carbon side of things. Indeed, this must be the one heteroatom proton. It's at around 1.7 ppm. Notice that is quite a ways upfield for hydrogen sitting on an oxygen in a solvent like deuterated chloroform. Now there's one other position on this molecule that I think is going to be pretty obvious, and this is the world famous septet of doublets. It's going to be this one here. It's the only position in this molecule that could ever have that extensive a coupling pattern. It is 3 bonds away from these 2 methyl groups. The 2 methyl groups, recall, even from the depth spectra, are not equivalent to each other, even if they're attached to the same carbon. This molecule is full of chiral centers, and so if the methyl groups aren't equivalent, the CH2s out here in the ring are not going to be equivalent as well. We're going to see a lot of that. But this one here, this one will be proton H, and a septet of doublets, and we can use the HSQC to tell us what carbon at position H is, exactly which carbon it is, and that allows us to fill in our table to this extent. And this covers the relatively obvious and fairly easy to get characterizations. One thing you're going to notice as we look at the next spectra is that with so much going on and so much to keep track of, that I go through every time I get a characterization and label it on my proton spectra, my carbon spectra, my HSQC, and even the Cosy spectrum, which is going to make its debut now. When I know where position F is, I label it in all those spectra, and position H and position K. Again, there's just so much happening that it's really, really worth your time to be very systematic and very careful with this stuff. Now that we've gotten the easy ones out of the way, the fairly obvious ones, it's time to move on from there, and this is where the Cosy is going to start strutting its stuff in this game. And so the strategy is going to be to go from one of the positions I know, and position F is a really good one here, since it is the most downfield, farthest away from anything, so it suffers least from any overlap and interference and second order effects and all that stuff that can affect the appearance of our spectra. And so position F is going to be the one that I'm going to start on, and I'm going to go to the Cosy spectrum and see what is position F coupled to. And what I'm looking for is, can I use it to find position D and position G in this molecule? And so I bring up the Cosy and I take a look at it, and I see that position F actually shows 4 cross peaks, and they're on both sides of the diagonal. I've highlighted them here. Now, one of the cross peaks is kind of interesting. It's actually back to the hydrogen on the oxygen. It's actually back to the alcohol proton. Now, really, the alcohol proton doesn't look like it has much coupling pattern to it, so it must be a very weak coupling constant, but the Cosy actually picked it up. There is at least a detectable coupling between them. Weak, but there. But that one I could eliminate, and that leaves 3 cross peaks to these 3 protons. So I pick one of them. I'm going to pick what looks like the strongest cross peak, the one at 1.9 or 1.95, somewhere in there. And it's either this proton at G or one of the 2 protons at position D. And so I use the HSQC, switch back and forth in Cosy and HSQC a lot now. And sure enough, 1.95 corresponds to a CH2 group. So what I found is I found the carbon in position D and one of the 2 protons out here. And this is where the HSQC really shines as well, because you'll notice that the carbon actually has 2 proton correspondences, the one at 1.95 and one much farther upfield, about 0.9. It's these 2 protons, and they are very different from each other. They are, 1 ppm different, 400 hertz different. This is a chiral molecule. This thing is not flexing. These 2 protons are quite different. We see the differences in the 2 methyls over here. We're going to see them in all the CH2 groups. But we've nailed down position D very nicely. And thus, we also now, by the process of elimination, know the position G right here. We know that proton. And sure enough, if we go to the HSQC, go from the Cosy, which gives us the last correspondence here, to the HSQC, we now know the carbon of position G. So we're getting our way through the molecule. Now at this point, when I can, I usually like to try to confirm things, just to make sure I'm on solid ground. And it's interesting when I do that, because this actually, doing this illustrates an issue that Cosy spectra can have sometime. And what I want to do is confirm that if this truly is position G, then it also ought to show in the Cosy a crosspeak, a coupling, to position H. Now this is the one of the obvious ones, the septet of doublets. We are looking for the thing causing it to be the doublet over here. And if you look at the Cosy, you do see a crosspeak. I marked it here, but then I run into a bit of an issue. In a Cosy, I should see a crosspeak on both sides of the diagonal. So I'm always in the habit of looking on both sides just to make sure. And this is where I ran into a problem. On the Cosy that I've been working from, I don't see the corresponding crosspeak on the other side of the diagonal. As the great Scooby-Doo once said, whoa, this could be a problem. I mean, it's an indication of there's a couple of possibilities here. One, my characterization as positions H and G and F here are wrong, and the experiment is telling me that I've gone off the rails someplace. It's not unheard of that happens. I hope it's not true, but be on the lookout. Or the crosspeak is weak enough, and while the 2 sides of the diagonal ought to be very similar to each other, in reality they're not always, that I may not have sliced into the mountain range quite deep enough when I put the Cosy spectrum together, that on one side of the diagonal the crosspeak is a little bit higher than the other, and so it shows up on one side but not on the other, and that's what's throwing me off. So you go back to the raw data just to see what's happening here. And so here is the Cosy spectrum again, but sliced a little bit deeper. You can see why I didn't keep this one, because it does look a lot noisier, but in the position where I would expect to see the other crosspeak on the other side of the diagonal between position G and position H here, I do see a crosspeak. It's weak, but it is there. So it's a little bit of relief to see that, so that it's pretty good confirmation that I do indeed have these 2 positions nailed down. Now given these parts, there's actually one more that is now going to be pretty easy to get. From the DEPT experiment, we have 4 CHs in the molecule. You realize now we've characterized 3 of them. We've characterized position H, position G, and position F. That leaves only one more CH out here at position B. And so there it is. We now know what carbon is at position B, and our HSQC again now tells us what proton is at position B. So our characterization table now has even more parts filled in. We've worked our way through a big chunk of this molecule. Now that we have these two positions, the hydrogen at B and the hydrogen over here at position H nailed down, the next thing we're going to do is try to figure out where the three methyl groups are. Get those characterized, and that leaves only the last couple of parts of the molecule to nail down. Now the methyl groups. I'm going to use our dear friend the Cosy spectrum and position H here, the septet of doublets. This is the one we know quite well, and use the Cosy to step over to the two methyl groups that it's coupled to, the ones that are giving the septet appearance to position H. And it's kind of interesting if you look at the methyl groups in here. There are three of them, and you'll notice that they're all clustered together, but one is separated from the others. One's a little over 0.7. The other two are pretty much over the top of each other at 0.8. And these two are the ones that are not over the top of each other. One of these is 0.7, one of these is at 0.8, and then the other one is also up there at 0.8. Now, that allows me then to find these two positions and the corresponding carbons. Now, in reality, I've labeled them I and J, and they have separate lines on our table that we're filling in. But with free rotation about this bond, is this one I and that one J? That one's actually a little bit ambiguous. Thinking about it, I might have better changed the table to have one row that had I, comma, J on it and just left it a little bit ambiguous. But I kept them separate in there, and what I've done is I've assigned proton I to be the slightly up field one at 0.75 ppm, and therefore the carbon at 16 ppm. Proton J to be the one at 0.82 ppm and 21 ppm on the carbon side of things. So by the process of elimination, I now know where proton A is, methyl group A, way over here on the other side. Now, A and J, as I've assigned them, are badly overlapped. They are not exactly the same, but they are badly overlapped. I think I can make a reasonable guess, looking at the Cosy and the HSQC, that proton A is the one that is on the slightly upfield side of proton J, and that cluster right around 0.8. One is slightly to the right of the other, and I think it's proton A that is slightly on the upfield side, but it's tight. It's hard to really nail it down. But when I fill out the table, I've assigned this one at 0.80, this one at 0.82, just to reflect that I think this one is slightly upfield of that one. Interesting, if you go to the HSQC and look at these two, if this one is at 0.8 and that one is at 0.82, look at the corresponding carbons. The slightly upfield one has the carbon that is slightly downfield. I assigned this one to the carbon at 22 ppm, this one to the carbon at 21 ppm. Slight reversal between the upfield nature in the proton spectrum versus the carbon spectrum. It's not unheard of. It happens fairly commonly, but it's interesting, and the HSQC reveals that very nicely. So we're almost there. Almost have the whole thing characterized. We're down to position C and position E, the remaining CH2 groups. We see them both in the HSQC. We see very nicely they're there. We see that the two protons on each of them are different. Two of the protons seem to cluster just above 1 ppm. The other two seem to be clustered in that awful mess below, around 0.8 to 0.9, all piled up in that methyl group. It's just a terrible overlap in there. Ugh. But what our strategy is going to be, we're going to go to a position that we are pretty certain about, and it's going to be this one, position G, here that we characterized a while back. And we're going to go to our friend the Cosy and look for a cross peak into one of the remaining CH2 groups. So we go to the Cosy and we find it. We find a cross peak from position G to that little group of things just above 1 ppm, and it seems to correlate to the one that is slightly upfield. So we're going to assign the hydrogen just above one that is slightly upfield of its neighbor to this one, to group E in the molecule. Once we have that nailed down, the HSQC will tell us where the other proton is and where the carbon is. And then, by default, because there's only one carbon atom we haven't done, we now know where position C is, where its two protons are, and where the carbon at position C are located. That allows us to fill in the entire table, and there we have completely characterized this fairly complex natural product, menthol, a peppermint extract. Now, in reality, can I be 100% confident that position A is at 0.80 and position J is at 0.82 and one of the protons down here at position E is at 0.81 like I filled in on in the table? Okay, they are so badly overlapped that probably not. I think they're reasonable estimates of their chemical shifts, but you know, they just are so piled in there together that they are just simply estimates. But that's recognized that that's just kind of how it's going to go in a molecule that has this kind of overlap. If we had a larger magnet, that would give us more hertz between every single one of these signals to work with. It would help us to spread them out just a little bit more, allow us to be a little more definite, and tackle even larger molecules. Someday, someday. But I want you to see how the 2D NMR spectra represent an order of magnitude increase in the power of this technique. It allows us to take molecules like this with terrible overlap problems and still be able to go through there and make our assignments and try to understand what's going on in there. It is truly one of the most powerful structural techniques we have available. And if you don't look at how this works and just simply stand back and be amazed at it, well, you just have no soul.